A stable amplifier begins with a stable DC operating point. In this lesson, we study voltage divider bias for a silicon NPN transistor. We will see how the divider establishes base voltage, how the emitter resistor supplies negative feedback, and how to calculate the Q point by exact and approximate methods. We will also test when the approximation is valid, compare errors, design a practical network, and verify operation against saturation and component limits. By the end of the lesson, you should be able to explain the stabilizing action of the emitter resistor, replace the base divider with its Thevenin equivalent, and calculate the operating point using exact analysis. You should also be able to test whether approximate analysis is justified, quantify the approximation error, design resistor values from a target Q point, and check active region operation, power ratings, and sensitivity to transistor beta. The quiescent point, or Q point, is the transistor current and voltage with no input signal. It determines how far the output can move before cutoff or saturation causes clipping. A fixed bias circuit depends strongly on beta, but beta is not a tightly controlled parameter. Voltage divider bias reduces this dependence by using a nearly fixed base voltage together with emitter resistor feedback. On the transistor output characteristics, the DC load line represents the combinations of collector current and collector emitter voltage permitted by the supply and resistors. The chosen base bias selects one point on this line. For an amplifier, we normally place the Q point well inside the forward active region so that the signal can swing in both directions without reaching cutoff or saturation. For DC analysis, all coupling capacitors and any emitter bypass capacitor are treated as open circuits. Resistors R1 and R2 form the base divider. The collector resistor produces a voltage drop proportional to collector current. The emitter resistor develops an emitter voltage and creates the negative feedback that stabilizes the operating point. These current and voltage relations will be used throughout. Collector current equals beta times base current. Emitter current is the sum of collector and base currents, so it equals beta plus 1 times base current. The emitter and collector node voltages follow from Ohm's law, and collector emitter voltage is the collector voltage minus the emitter voltage. Suppose temperature or device variation tends to increase collector current. Emitter current rises with it, so the voltage across the emitter resistor increases. Because a stiff divider keeps the base voltage almost constant, the base emitter voltage is reduced. This reduces base current and opposes the original rise. The same loop acts in reverse when collector current tends to fall. A divider is called stiff when its current is much greater than base current. Under that condition, connecting the transistor produces only a small reduction in divider voltage. This is the physical basis of the approximate method. The exact method includes base loading and remains valid even when the divider is not stiff. There are two common analysis routes. Exact analysis replaces the divider with its Thevenin equivalent and includes the base current loading. Approximate analysis treats the divider voltage as unloaded and assumes collector current is approximately emitter current. The approximate route is faster, but it must first pass a validity test. To form the Thevenin equivalent, first determine the resistance seen from the base terminal. Deactivate the ideal supply by replacing it with a short circuit. Resistors R1 and R2 then connect in parallel. This gives the Thevenin resistance used in the loaded base loop. Next, open the transistor input and calculate the divider's open circuit output voltage. This is the Thevenin voltage E sub Th. The original supply and 2-resistor divider can now be replaced by one voltage source in series with one resistance. Apply Kirchhoff's voltage law to the Thevenin source, Thevenin resistance, base emitter junction, and emitter resistor. The voltage drops are base current times R sub Th, the silicon base emitter drop, and emitter current times R sub E. Substituting emitter current as beta plus 1 times base current gives the exact base current equation. The exact procedure is systematic. First, calculate the two Thevenin quantities, then solve for base current in the loaded loop. Use the transistor current relations to find collector and emitter currents. Calculate the emitter and collector node voltages separately and subtract them to obtain collector-emitter voltage. Finally, verify that the transistor is operating in the intended region. A numerical answer is not complete until the operating region is checked. In forward active operation, the collector node should be above the emitter node, and collector-emitter voltage should be comfortably greater than the approximate saturation voltage of 0.2 volts. The base emitter junction is forward biased, while the base collector junction remains reverse biased. Consider a circuit with a 22-volt supply, divider resistors of 39 kilo ohms and 3.9 kilo ohms, a 10 kilo ohm collector resistor, a 1.5 kilo ohm emitter resistor, and beta equal to 100. We use a constant base emitter drop of 0.7 volts. The parallel combination of the divider resistors is 3.545 kilo ohms. The unloaded divider voltage is exactly 2 volts. These two values replace the original divider when we analyze the transistor input loop. Substituting into the exact base current equation gives 8.384 microamperes. Multiplying by beta gives a collector current of 0.838 milliamperes. Using beta plus 1 gives an emitter current of 0.847 milliamperes. Calculate collector-emitter voltage using the collector and emitter current drop separately. The result is about 12.35 volts. Therefore, the exact Q point is collector current 0.838 milliamperes and collector-emitter voltage 12.35 volts. The available voltage margin confirms forward active operation. The common screening rule compares beta times emitter resistance with 10 times R2. It estimates whether the resistance looking into the base through the emitter network is large compared with the lower divider resistor. If the condition fails, use exact analysis. Passing the test does not make the approximation exact. It only indicates that loading should be small enough for hand analysis. For the 22-volt example, beta R sub E is 150 kilo ohms while 10 R2 is 39 kilo ohms. So the approximation is acceptable. Approximate analysis gives 0.867 milliamperes and 12.03 volts. Relative to the exact values, the current error is plus 3.4% and the voltage error is minus 2.6%. The stabilizing effect can be seen by repeating the exact calculation at a much lower beta. Halving beta from 100 to 50 changes collector current from 0.838 to 0.812 milliamperes, only about 3.1%. Collector emitter voltage changes by about 2.7%. This is far less than the 50% change in beta. As an exercise, perform the calculation with beta equal to 50 to verify the shown values of ICQ and VCEQ. Now consider a weaker divider with beta equal to 50. Beta R sub E is only 60 kilo ohms, while 10R2 is 220 kilo ohms. The validity test fails. Base current significantly loads the divider, so the exact method must be used. Exact analysis of the counterexample gives about 1.98 milliamperes. The unloaded divider approximation predicts 2.596 milliamperes, roughly 31% too high. The error occurs because base loading lowers the real base voltage. Thevenin analysis captures this effect through R sub Th. For this design, target 1 milliampere and about half the supply across the transistor. Choose emitter voltage near 10% of the 12-volt supply to provide useful feedback. This gives an emitter resistor of 1.2 kilo ohms. The remaining voltage allocation gives a calculated collector resistor of 4.8 kilo ohms. So choose the standard value 4.7 kilo ohms. The target base voltage is emitter voltage plus 0.7 volts or about 1.9 volts. With minimum beta of 100, the estimated base current is 10 microamperes. Choose lower divider current near 10 times this value. The calculated R2 is 19 kilo ohms, so choose 18 kilo ohms. Accounting for both divider and base currents gives a nearby R1 value of 82 kilo ohms. Always verify a design using exact analysis. With the selected standard resistor values, the Thevenin resistance is 14.76 kilo ohms and the Thevenin voltage is 2.16 volts. Exact calculation gives collector current 1.074 milliamperes and collector emitter voltage 5.65 volts, close to the targets. Perform simulation using LT-SPICE to verify the values shown here. The approximate DC load line runs from collector current 0 at collector emitter voltage equal to the supply to the saturation current found by dividing the supply by the sum of collector and emitter resistances. Confirm the Q point lies inside this range. Then check transistor dissipation, resistor power, beta limits, resistor and supply tolerances and temperature dependence of the base emitter voltage. Voltage divider bias works because the divider establishes a nearly fixed base voltage while the emitter resistor supplies negative feedback. Exact Thevenin analysis includes base loading and is the reliable reference method. Approximate analysis is efficient only after the stiffness criterion passes. A complete design chooses practical resistor values, verifies the Q point exactly, and checks region, power, tolerance, and beta sensitivity.